I have a question.
Yeah, please go ahead.
Will you go into in the transformer architecture? Will you go into any flash?
Today, not today. Today it would be a stretch goal, but I'll be happy to do an extra session for that if that interests you. And there's a point, I'll come to it in a moment. All right, folks, welcome back. Today's topic is about attention, self-attention, and transformers. It's a big topic. We are going to cover a lot, and I do request that you all pay well attention. Excuse the pine. So this concept of attention came out of Google in 2014. About the same time that generative adversarial networks came out and ResNet came out and many other big things came out. At that time, it did not garner as much, well, attention as perhaps it deserved. This topic, so we will give some amount of time today to this topic, attention. Now, I want, at the outside, I must say that there are three different things. And transformers that we'll talk about. Now, people often get confused between attention and self-attention. Indeed, most of the explanations of so-called attention is actually not about attention per se, but it is about self-attention. This is one of the fallacies that you see in the videos and a lot of the literature. And perhaps the reasons are understandable because self-attention is a core part of transformers, and transformers are dominating the scene. So whenever people talk of attention, so quite often they mean self-attention. But today we'll go back to the original concept of attention. Now, one book that I liked very much, of the many the references I gave you as textbooks, the one book that does talk about attention in a very clear way and the correct way is the book Inside Deep Learning. It's one of the textbooks, if you remember, for this course. Inside Deep Learning is the book I would strongly recommend you use to review attention itself. For there is another thing that I would recommend, and I put it on your course portal. I have access to it. I'm not sure if you do have access to it because that video may or may not yet be public. It is still in the making from the great explainers, the 3 Blue 1 Brown channel. They are making this video on attention. That video is on your course portal at this moment under the attention section. You can check whether you guys can see it or not. I can't tell because I have a membership to that group.
It's available.
It's available. Okay, you can see it.
Yeah.
Excellent. So I would say that the two references you should use is the 3 brown, 1 blue. Oh, sorry, 3 blue, 1 brown. 3 blue, I always get it mixed up. 3 blue, 1 brown. Wouldn't have been easy to remember. 3 apples, 1 orange. Brown and then video. And inside deep learning textbook. Inside deep learning textbook. These are the two things I would strongly recommend. One second. On transformers, once again, there is a 3 blue, 1 brown video that is absolutely wonderful. Right? Very, very clear explanation of it. You should watch that. And the question today would be, after such excellent introductions, am I entirely superfluous? That was a thought with which I walked into this room. What possible use do I have re-explaining all of this when such excellent material exists on such very, very important topics. So I'll let you guys be the judge after you have listened to my half a minute. Go ahead.
Yeah, I actually did watch this video, and that was where I came across KV cache and KV matrices, and I have questions, so I don't think it would be superfluous to move forward.
Yeah, it wouldn't be superfluous. It's just that given the fact that we are a 3-hour session, we are quite likely to run out of time. We also pedagogically have to lay the foundation for easy stuff. But how about that? Before I start, I'll just in the break you can come, or right after the class you can come. The KV caching is a very important concept because it brings about efficiency, especially because we are talking about decoders, etc. these days. And I will be happy to explain. Or what we can do is we can do a regular 3-hour session, and then I'll be happy to extend it by another hour for those of you who are interested, and we can work our way through these interesting topics. So let's see how the evening pans out. But I have absolutely no hesitation in going into those territories, that and rotary positioning and all of that. Okay, so let's start with attention. Attention, when we talk of attention, the concept is as intuitive as life itself. We pay attention all the time. What is attention? If I were to ask you, forget about computer science, forget about neural networks. In a very simple way, what is it? What does attention mean?
Listen.
To listen. But deaf people too can pay attention.
Wait.
Come again?
Wait.
Wait.
Tension.
Tension.
No. Okay. Well, I went through this topic, that's why I'm saying that it was wait.
No, in common language, forget it. You're not you're talking to a 10-year-old.
Focus.
Focus. Focus. Let's go with the word focus. What is it to focus? You just replaced it with a synonym. Well, not an exact synonym, but what is it to focus? Live in the moment. Well, now we are getting into mindfulness.
You're looking at a narrow slice of things, ignoring the aspects.
Bhavin says we're looking at a narrow slice of things, ignoring other things. So, any other explanations?
You're trying to look at the sense of it, the sense of the subject, and ignoring the rest. So basically, if you have a vast set of
Focusing based on the context and the waiting.
Definitely, I've read about the details. I'm asking as a common layman. Yeah,
Concentrate.
to concentrate.
So if you take a picture example, maybe if you have a camera, you have wide field of vision. You will take your bird, that is my focus. I'm just only focus on that one.
Yes. So you guys are all getting it right. I would like to hear some commentaries from those of you who are dialing in on the Zoom. There is a thundering silence on the Zoom. Anybody?
Attention is the ability to focus on a portion or a section and perform functionality against it. And by having that focused attention rather than boiling the ocean, we're able to do very efficient parts. And in the aggregate of that, the efficiency is substantially better.
Yes, that is one.
But I'm cheating because I'm in the Sunday class, so that's why I'm not saying anything.
All right. Anyone else in the remote who would like to speak up? Yes, that is true. I've gone over this territory in the Sunday class. Anybody else? So, guys, I'll give you a real life example. Your instructor, that is me, goes out hiking most mornings. Today, actually, I didn't. I tried to go out and came back because yesterday was very hot and I got a heat stroke. But When I go out early in the morning, it's still dark sometimes. Stars are still out. So I walk along a river, a creek actually. It's more pretty wide creek. So it's called the Alameda Creek, though in winter it becomes a full-blown river that opens out into the bay, that pours into the bay. Now, there is a part of that creek journey where I start is the end of civilization. So the first mile you still see, if you look to your left, to your right, you still, not first half mile, you still see a couple of houses. After that, it is pure wilderness. So imagine that I'm happily going there with my hiking pole every morning. And it's quite delightful actually. Then at night, everything is quiet. These days, there's mist over the creek. And as you walk, there is the expected, there are two owls actually. One owl on my left on a tree, and another owl far off, not on the creek, but somewhere else. And I suppose one owl always hoots to the other. And my wife said, told me that one owl is telling the other that the third one is here. So,
So be careful.
yes. So now what happens is I sort of watch out for it. I'm waiting for it at that moment. It's just fun to encounter that. Then I move forward and there's complete silence. Then I go under a tree and I know what will happen. There are lots of birds sleeping in the tree. When I started hiking, I used to carry a flashlight with me. And then I realized that it disturbs them. So I would turn off. Now I don't carry a flashlight. Just walk. Right? Like this. And then as I keep walking, and by the way, this is obviously in California, there's always a risk of rattlesnakes. In case you're worried about that, don't be, because rattlesnakes, I happen to know scientifically, they don't come out till the temperature exceeds at least 75 degrees. They're reptiles, they're cold-blooded, so you won't get snakes. So you continue walking forward, and then gradually you hear the mowing of the cows in the distance, and the birds start chirping, and life begins to wake up. But suppose, and I'm looking at that moment, the pleasure is to, first of all, see the stars disappear, to see the mist on the creek, to see the sunrise, and all of that are beautiful to see, all the color. Actually, the most beautiful moments happen, unfortunately, before the Silicon Valley blokes wake up. Right? So, and they miss it all. No wonder so many people have to go to a psychiatrist for depression treatment. They miss the best parts. Anyway, jokes apart. Suppose I were to hear the sound. Whoa. What would happen? The sunrise, the hills, the mist, the creek, the bird chirping, everything would disappear from my consciousness. Why? It's life preservation. The context has changed, isn't it? Suddenly, you're in a fight or flight mode. You're holding on your hiking pole and looking all around. Where did that sound come from? And this is lion territory. These are mountain lions. They are rare, but they are there. Actually, just 3 weeks ago, another hiker observed their paw prints and he convinced me that they belong to the big cat. So what happened? My attention was wide. In the beginning, my awareness was pretty wide. It was covering, as I said, quite a bit of the beauty of nature. But just one wow, and it's all gone, isn't it? It's in survival mode. The context changes. And the context did what? It completely made me to focus on the sound, which means, but did the hills and the river and the mist disappear? They didn't disappear. They're still there. But our mind is not on them. I'm not putting any sort of gravity to observing them. All my attention is, where is that? I'm looking at every bush along the river creek. Right? That is attention. That is, I'm attending namely to only one thing. The roar, the sound of the cat, big cat. Right? And trying to figure out, or whatever it is, there are coyotes here. This is literally called the Coyote Hills. Is there a coyote? Is there a mountain lion? Or what is it? Right? So that is to pay attention. When you go with a friend to a bar, it's noisy, isn't it? Or you have a cocktail party at home, or a party at home, it's noisy. People often use the word cocktail in the textbooks, but I suppose since most of my audience is teetotalers and they abstain, so I would say any party. Well, the good thing with engineers is they don't need to be inebriated to be loud at parties. They get animated pretty quickly. So you guys are very animated. But have you observed that despite the din of sound, the whole above the cacophony of all of that, you are still able to hear the person you're talking to. Why do you think that happens? A machine is not able to. If you were to just put a microphone, that microphone would not register what your friend said any better than it would register the cacophony of the party. But your ears, you pay attention, but your ear is just an eardrum. It is no different from a microphone. Microphone has a diaphragm, so does your ear. Your inner ear carries that message to the brain. But what does your brain do? Of all the pieces of sound that it is listening to, that comes to it, it is somehow able to listen to and pay attention to your friend. Am I making sense, guys? Another example, you can attest to that. Usually in your house, there are all sorts of sounds. The refrigerator hums. Outside the house, the cat meows. Right? Things like that happen. And in some homes, inside the house, the cat meows. Right? Many things happen. Then, as parents, if you have a little baby at home, the moment the baby cries, all your attention is on the baby now. So why? Because you cannot ignore that. You have to. There must be something happening that needs attention. And these are classic examples of paying attention. So let us quantify that. Attention is, suppose you have a whole set of things, set of information, right? Let's say x1, xt, x2, x3, all of that. You happen to pay attention to some xk, isn't it? Maybe a little bit of attention to x2 also. So it is from the inputs that you get from inputs, put differential importance to a subset. That is attention. If you ever, those of you, and these days it's common, I don't know how many of you ever do that. If you were ever to go in what in the West we call mindfulness, what is it that you pay attention to? Usually they start you out, the primer is that you pay attention to your breath. Why is it, then what is it? But every time you pay attention to something, the subtext is you're not paying attention to something else. What is it that you're trying not to pay attention to?
Thought.
Yeah, the cacophony of inner chatter, mental chatter and thoughts. It is there, you can't stop it. They don't tell you stop thinking. It is the natural function of the brain to continue to think. Right? It's the excitation of the brain, thoughts, emotions that keep pouring through. But the most elementary thought exercise you are given is to pay attention to something that is literally, indubitably, undeniably a reality in front of you. Unquestioningly true, namely your breath. So that is attention. And so we'll start with that. Given given why is this relevant? And it is surprising that it took so long for people to come upon it in hindsight, but they did. And this paper, I would say, of 2014 is perhaps one of the somewhat, in my opinion, underappreciated work. Let me give you another example. Suppose you look at I ask you, what object is it? Is it a house? Is it a boat? Or is it a child? Or one of the many other things. And there you have this cute kid. What will you pay attention to? What gets attention in such a situation? You say that, hey, this very, very clearly is a kid. Why? You will end up paying attention to which part of the picture? This. This is a giveaway. Right? You see the kid with eyes and nose. The rest of it, yeah, matters. But actually, even if the rest were not visible, you would still recognize it as a kid, isn't it?
I think it's not that the context, it never depends on, like, hey, you're looking at warships. You don't look at a child at the point, look at what kind of ship they're going to do.
That is right. So the context determines what it is. So if your job is to tell, is it the context there is to tell what is it. So let us lay it down. A context. A context is important. It sets the purpose, the background, the context, and then differential importance to inputs. That these are the two key ingredients mathematically of attention. So with that, let us bring it down a little bit and make it more concrete. One of the lovely examples given in your book, and I'll literally use that example as a starting point, is this. Suppose what they did is they said, let's look at the MNIST. See, all great things have to start with MNIST. Is the hello world of deep learning. Right. So MNIST is made up of digits, let's say 0 to 9, 10 digits. Are we together? Now, in this data set, usually the most elementary problem is, given a problem, let's say 8 is written here, you have to pass it through a neural net. You can pick your neural net, CNN. Well, obviously it's about images, so you probably will pick CNN, let's say. But just for the sake of argument, I'll take something simpler because I want to explain the concept. I'll just take a feed forward. A density, right? And then you have to classify what is it. What will the last layer look like? It will be a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What will this last layer be? A softmax. Okay? Because you will get 10 logics. 10 logics. And then you have to convert all of these into a probability of 0, probability of 1, all the way to a probability of. So this is easy by now, right? This is a simple discriminative task, discriminative learning task. Given 50,000 training data, you can do it and you can get pretty good efficiency. If you do a feed-forward network, a simple feed-forward network, let's say that you achieve an accuracy of, let's say, 92%, not bad, or 90%, whatever it is. I don't know the exact number, but let me just say 90-ish, 90-ish. Accuracy. Now, when you have it like that, it is good. Now, let's make the problem a little bit more difficult. What you have to do, remember I asked you guys a problem. Given a set of numbers, find the max. Do you remember? That was a quick one. You didn't have to do anything at all. All you had to do was remember that there is something called a softmax. That's what the last layer does. Right? But now, suppose I give you a few images. Right? Image 1, image 2. You don't know what's written on them. And let's say arbitrary number of images. Let's say that 10, some images. 5 images. Let me just take a fixed number, just for the sake of one. Fixed. 5 fixed. I 5. 5 images. In those images could be any number written, any of the digits written. Are we together? Let's say that this one has 9, this one has 3, this one has 2 written. And I ask you a different problem. I ask you which of these is the largest? Which of these images points to the largest number? You see, I changed the game, right? You have to point to the largest. Now you can, oh, by the way, I take this back. Just a simple classification of this would be high 90s, 90, okay, 99x, 90, some high 90s, 95 or something. Right? But when I give this problem, you would probably barely get about 90% or even less accuracy, because the problem is hardest. I'm not asking what is this digit. I'm asking, among the sequence of things I've given, which is the largest digit? So 2 things are needed. You need to recognize what it is, and you need to tell which of them is the biggest. You see that, guys? Huh? So you can, of course, create a training data from the MNIST, derived from MNIST, and feed a feed-forward network and train it. But you realize that what you need to do is be able to, in reality, tell that the smallest one, for example, it cannot be this, that it cannot be this. Do you realize that if something is less than average, it cannot be the answer? Right? Am I making sense? This is how you solve your multiple choice questions. This is literally for the machine a multiple choice question. Which is the largest? And so, how do you solve it? You first eliminate the choices that don't make sense. And so, suppose you could do this. You say, all right, what we need to do is somehow make the machine pay attention to this guy. Somehow. Turn the mind's eye. After looking at everything, it should be staring at the right answer. Paying attention to it. Right? So how do you need that? To pay attention, it needs a context. Right? The context is these numbers. Now, but these numbers are many numbers. You don't know how many, but in this case, I said 5. But one thing that if I were to say, let the context be, context has to be a vector, because, well, networks act upon vectors or something. If you had to create a vector out of vector, let me just call it H vector. Right? Or no, let me not call it H vector. Let me call it all right, I'll call it the C vector, context vector. Right? Now, think about it this way. Suppose I have a neural net just made up of feed-forward networks. I give it all of these images. Right? At the end of it, for each of these images, I will end up with a hidden state. I can convert it into, so here is the network. It will end up with a hidden state, right? H1, H2, H3, H4, H5. Let's say I gave it 5 images, 5 vectors. That part is straightforward. Isn't it? I flatten each of these images and I feed it into the system. I will end up with 5 vectors. Does that make sense? And now what can I do? These are all vectors, so this is good. Now let's think about it. What is the easiest vector I can create out of these vectors?
average of the vectors?
Right. What you could do is you could just say, let's take the average or the sum or something like that. Let's take the average vector is equal to 1/5 of h5. Make sense? Summation over plus h5. So you compose something that is representative or is a statistic on the whole bundle of vectors. You can do fancier things, but let's start with that. You say this h bar. And now what you could do is you have these vectors. Each of these vectors may be pointing into different directions. You took the average vector. Right? Now what can you do? You can do, and this is the part that is interesting, you can say, I want each of the hidden vectors, I want to see how much attention to pay to each of the hidden vectors. Right? For whatever reason, let's say I want to do that. So what you do is, an easy way to pay attention would be to see how aligned is each vector to the average vector. Now, there's a little bit of math and there's a thing that I'm sort of glossing over, but take me on faith because I don't want to go into quite a bit of math. So you agree that I can create a score function or a score, let me just use the word score, which could be just the dot product between each of the score I is the dot product of that. And let me call it the C. Context is C, right? Context. Let me just say C. And the C vector. So far, so good, guys? Now, once I create this particular thing, then I can say that how much attention I need to pay, like how much relevance I need to give to this vector. Let me take it as is literally hi c times the vector itself. And then what I do is I say, okay, I have a machinery that will produce, because it can compute C, I call it the attention level. What comes out of each of these? What comes out of these will be AI. Now, why? I've glossed over it, right? A little bit, A2, A5. 5 vectors will come out of this, isn't it? See, the dot product will give me what? A number, a score. Dot product between 2 vectors is just a number. And then I say that every vector will either become big or small, shrink or grow, right, based on its alignment to the context. Right? So now what happens? I started with these vectors, but let us say that the average vector, these two look big. In this case, let us say that the average vector was going in, let me deliberately increase the size of some of these. So suppose this is it. So let's say that the average vector was going like this. Does it look reasonably like the average? This thing. And so what I'm doing is, some vectors will, or whatever, I mean, I've made it too fat. Let me make it a little bit thinner. Yeah. So this. So now what will happen is, these vectors, their sizes will change and shrink. Right? Because hi goes in, what comes out actually is rather discolored. Hi goes in, but what comes out is another vector, ai. Right? It is in the same direction of h, but you have scaled that vector. Now you say, well, why did I do that? It turns out that if you put this, see, initially what were you doing? You were taking all the hidden states, these were your hidden states, right? HIs, that you were putting it through the softmax. But it turns out that if you make each of the vector discover its alignment to a context and based on that shrink or grow, it is almost like I am the mist vector. Let's say in my hiking example, I'm the mist vector, and it turns out that I'm not terribly relevant to the roar. Shrinks. Are we together? Another vector is, so end result would be what? That if you do your thing, and obviously I'm giving a very hand waving argument here, there's more to it. If you feed this into yet another layer, so I mean, while you're at it, you might as well feed it into another feed forward network if you want to, at least one or two there, and then go feed it to the softmax. Now you realize that we have introduced the most elementary form of attention in some sense, like just something to say this is the context and how aligned are you to what it is about. Right? Just the sheer act of doing this, you will notice that your accuracy jumps. Model accuracy jumps by a significant amount, jumps significantly. When accuracy jumps significantly like this, you know that you have caught on to a good idea. Are we together, guys?
So is it that inside pattern do the average?
Come again?
I mean,
So here, this particular example, because it's there in your textbook, it said that, we need to create one vector out of all of these inputs. Let's take the average. But you can be more clever. You can do other things. There are other things you can manufacture out of it. Create a context vector somehow. All it is saying is, if you introduce an attention step, immediately you notice that your classification goes up. Right? Which thing
so
is
in the training, we will be giving that as a context vector.
No. It will figure it out. The scoring function, the scoring layer, this layer.
No,
so how does it look?
C is we are calculating. So calculation is mathematical operator.
No, so let's go through this. We gave it 5 images. The first layer is a feed forward layer, feed forward network, right? Then you feed it into what I call the attention. What will it do? It will compute two things. First, number one, compute the C. How will it do that? You literally hardwire it. Whatever comes in here, you put a little step here, a function here. C is equal to H1 plus H2.
Yeah, so that's why
You hardwire it.
Yeah, generally like in the machine learning.
Yeah.
We don't do this like mathematical calculation.
No, you do that. Yeah. So in this particular case, there are many problems you can solve in deep learning, in which at a certain stage, you just decide that the information that is coming in, I'm going to apply this transformation to it, or I'll extract this from it. You do that, and then what you do is you compute the score. You compute the score, and then third step, you compute the attention. And then you let attentions go up. And then while you're at it, you may want to feed it to another feed forward network. If you wish, you may or may not wish. And then your normal softmax to figure out which is the largest, which image represents the largest. Yeah.
I didn't understand the part where the score is computed by using a dot product of HI and context.
Yeah.
How does it actually give the score? I don't understand that part.
See, when you take the dot product of two vectors, what do you get?
For another vector.
Now, you don't get a vector. Dot products never give you a vector. They give you a number. Dot products produce a scalar value. So this is a thing to remember. Dot products produce a scalar value. In other words,
dot product is different from matrix multiplication.
Oh, matrix multiplication is entire vectors, dot product of vectors. Remember, dot products work on vectors, not on matrices. Go back to your middle school mathematics. Where is vectors taught in schools? It's not.
High school, high school.
High school. Go back to high school math. Right? Go back to high school. Right? Dot products produce a number.
Okay, so and just that scalar value is the score and it will work.
It works magically.
I'm not getting the
But there is more to
why
it. So I'll tell you why. I'll give you the intuition. I don't want to go into the math. I'll tell you why. See, imagine, right, that there is a vector that somehow contains the context that really matters to you. Here, for example, these numbers, right? Each of the images has become a number. You're training the network. These vectors are what they're trying to do is they're dissipated in different directions. But let's say that there is a direction. There is a direction that represents the direction of forward of the large something, or is the average direction. See, you dot product anything with the average, what will happen? Well, what will happen is if you take a random number of vectors, just try to dot product them randomly. They will give you how aligned they are with the average, how much they are pointing in the direction of the average, and how big they are. So what happens is that what it will do is take that score and multiply each vector by that.
Type of squaring the numbers.
It is basically saying, hey, I'm going to take every vector and either stretch it or shrink it based on how aligned it is with the context. So suppose you end up with three vectors, let's say three vectors, three initially, right? Then based on the attention score, one will become small, one will become big, and one will become like this. You resize them.
Please come again on that. What is it? Go big or small?
Yeah, see, if the dot product is, let's say, 0.2, then multiply anything by 0, any multiply by 0.2, you shrink it. Right?
But how you said that, how is it going to become shrink or elongate depending on the
Suppose the dot product is 3. You make it 3 times. What if the dot product is, let's say, minus half? It will now start pointing in the other direction.
So the dot product is for every pair of values? Like,
Yeah.
how
The
do you
dot product is between every vector and the context. Remember, the definition of, and this is it. This is the most important thing that people don't quite get, that the whole attention comes from these two equations. This is what attention is. Right? What you do is you take every vector and you say, I'm going to scale it by a score. Right? And in the process of scaling it, it may even start pointing in the other way, the opposite way. It may shrink or it may just turn upside down. So in a good neural network, what should happen? For this particular problem, you would rather that in whichever is the biggest digit pointed to, it stands out from the other ones. Other ones are pointing, they're looking all sorts of ways. This one is looking the right way. Right? Then you feed it into another network, etc. And then you do a softmax. You get a cleaner separation. So you observe that it's a cleaner separation, right? And people did that with images, and you could see that if you brought this, even with CNNs, etc., you brought this, then the machine started paying much better attention to those regions of the picture that matter, like the face, when it would do classification, right? Or if it was an automobile, the wheel, right? You could literally empirically say that the context, different situations have different contexts. In this very elementary example, the context was easy, just average it out. But the most important thing is of attention is that you need 3 things. You need a C vector, context, vector. You need a dot product, of every hidden state with the context. This is a dot product. This is my way of writing dot product. This will produce a what? Score of the ith vector. And then you have attention, which is the score I. Let me just call score I, SI. SI times HI. This is the, what is this? This is the attention vector, because this is the vector. If you multiply H with this, you get an attention vector. Now, guys, it's not something you'll get. There's a lot happening here, and I'm just trying to give you a rough intuition. It will leave you with questions. It should leave you with questions, unanswered questions at this moment. Go ahead.
How do you decide what the context vector is? It assumes that you know what your inputs are going to be, or what class of inputs.
In this particular case, yes, but as you will see in the subsequent examples, there are ways in which you make the machine learn the context itself. In fact, that is where the self-attention comes in. We'll come to that.
So that was my original question.
Yes, and we are coming to that. So guys, I want you, the reason I dwelt upon this topic is not many people realize that attention and self-attention are different things, right? But at core, this is attention, all right? Given this as attention, now let's come to self-attention.
So just from the intuition standpoint, that facial recognition example you mentioned.
Right.
What would be the context you would set for that? For the facial recognition.
See, with facial recognition, it's a little bit more complicated with CNNs, right? You let it discover. So this was an example of numbers, right? So I told you, even if you start with a very basic context like this, it works. In the case of CNNs and facial recognition, it's a little bit more complicated, and there are lots of papers that go into it. But roughly speaking, you let the machine discover its context from the feature maps. That's it. So, okay, now let's come to the concept of self-attention. The self-attention paper also came from Google in December 2017. And the title of the paper was very interesting. It was Attention is All You Need. A pretty provocative paper, and there's an interesting bit of history to it. When attention was discovered, here is how the world stood. For computer vision, the king of the hill used to be CN. Convolutional networks. And for natural language processing, the king of the hill used to be RNNs, recurrent. It's a neural nets, LSTM, GRU, which are like sort of more evolved versions of a basic RNA. Then these guys, the problem was this. The filter, the convolution operation was massively parallelizable, right? And so you could use the computer graphics card, GPUs from the GPU companies, NVIDIA, AMD, etc., to accelerate the CNNs. Are we together? See, you have 50 filters. You can apply all the filters in parallel on the input. Nothing stops you, right? You can go sliding all over the place, and you can do a lot of operations all in parallel. It is only in your mind that you think that with a filter you're moving like this, isn't it? In reality, you can do all the computations for all the strides all in one go if you wanted to, if you had enough memory to do the matrix multiplications. It's just a whole lot of matrix multiplications, each independent, to produce the result. On the other hand, natural language processing had a bit of a problem. the problem natural language processing had is you had this, you would pass it a hidden state, right? You would pass it an input. It would be in a hidden state. You would pass it an input x3. It would have a hidden state, and then it would produce the next hidden state, h next, right? Based on the next input that you gave it. Are we together? And you had to give it the tokens one at a time. And then, of course, you had the output. And if you were doing decoding, then you had to feed the output back into it and all of those things you had to do. The whole process was sequential. It was a sequential machine. So many things were problematic. People tried to create deep recurrent networks. They were failing. There was nothing deep about recurrent networks. 2-3 layers, even that, maybe. The other thing was that the whole thing was a sequential machine. So what do? People puzzled over it. And so this was the history of the field. At Google, they began to do funky things. They said, okay, there is a CNN, we know. There is a recurrent, we know. The big problem they were trying to solve is natural language processing. How do we accelerate it? Now, it turns out that recurrent, here you can actually apply CNN. One dim CNN, for example, can be applied, etc., etc. You can adapt CNNs to do words also. So people tried CNN, they applied RNN, and then they said, okay, let's bring in attention. But okay, even before that, there's a bit of history. What people realized is when they discovered attention in 2014, they realized that if to this you add attention, the results get better. Are we together? CNN, add attention, it gets better. RNN plus attention, it gets better.
Even for the
natural language processing.
Even for the image processing.
Yeah. So basically the idea was that whatever plus attention, this was the observation, is equal to whatever plus. Much better results than you would get from whatever. Whether it was feed-forward network, it was CNN, it was RNN, it was LSTM, well, this whole family, LSTM, GRE, etc. Just throw in attention, it gets better. Are we together?
CNN, filter itself is kind of attention. Just pointing some space, pointing that area that we are not considering.
That is right, yeah.
That is attention.
That is attention, yeah. So then what happened is these guys at Google, they were trying to solve actually a computational problem. How in the world do we make it faster?
Sorry, I think your question is about the kernel.
No,
Which
I'm
is-
questioning about the filter.
Yeah, that's what the kernel is moving to create a feature map.
No, that is not attention.
Yeah, okay.
Remember, attention is always, it needs a scoring function.
Okay, it's a separate.
It's
So
a separate.
after you pass
Yeah,
the
yeah.
create a feature map, you have to
Then
apply
you-
the score.
After
That's yeah. So guys, this was the state of the art. This was well established that if you did this, it worked. Till 2017, people were throwing in attention everywhere, but they thought attention is this little advanced topic that if you add it to things, they become better. So these guys who were sitting at Google, they're forming teams and they were just poking all around it. They threw in CNN, they threw in RNN, they threw in attention. So they were literally doing this, right? And getting somehow for the whole thing to work. Till they started observing something. And this is how things are discovered. They started observing that what happens if from this very complicated architecture that we have created, right? And they were giving it all sorts of names. Historically, I think they were calling it cargo, right? Convolutional, right? Attention, recurrent, GoogleNet, right? They're literally thinking words like that, cargo, apparently. So it seems from one of the interviews that I listened to. So nothing left behind, right? convolutional, attention, recurrent, and of course GoogleNet.
That's self-driving cars.
Come again?
They had self-driving cars at the time for the car.
Yeah, cargo. Yeah. So anyway, as they were cooking up acronyms for their network, they began to observe. Apparently, from what I can make out, is that what happens. It's called ablation studies.
Finally, it tells particular matters and it's all accident.
Yes. So what happened is that they realized that what happens if I remove this? Well, it turns out it works just as well. You remove RNN. The great surprise was without RNN, it worked just as well. CNNs are parallelizable. LSTMs, GRUs, you remove them. The whole thing worked as well. And to boot, you could even parallelize it because the single biggest bottleneck, the sequential bottleneck, was just gone. You see that, right? And so if from cargo, you remove this and you remove this, what remains? Attention, right? And therefore the title of the paper, Attention is all you need. In other words, you can create a pretty good natural language processing engine, a language model. These are called language models. And I'll explain what the word language model means in a moment. To create a language model, you can do it without CNN, without RNN, without LSTM, without GRU, without any of these things. All you need to do is just keep attention. Right? And this is how, through experimentation, they discovered. And if you read and we will walk through the original paper now shortly after this, after I've explained the concept. It's a landmark paper and it's worth going over at least in a brief way. The whole thrust of the paper and the researchers was, oh my God, we got away with just attention and see all these natural language processing tasks. It is meeting or exceeding the benchmarks, right? It's reaching the state of the art. Reaching and beating the state of the art on the various benchmarks, on various tasks. And when they realized that, they knew that they have come upon something very interesting. They were quite excited about the biggest fact that it could be parallelized. Right? For the first time, you could say almost that you created a language model architecture that could be massively parallelized on the GPUs.
I get it, but like we needed the next token to be hidden to now to get the next token.
And I'll explain that in a moment. Okay. Right? So I'll explain that. That's a mystery. Hold on to that. Okay. So guys, are we getting the point? But I haven't explained what is it that they did. Actually, the word it's not attention. What they used is actually self-attention. So maybe a more, I suppose, precise typing, self-attention is all you need. Right? So what does that mean? I notice that some of you are walking around and taking a break. So how about this? I give you guys a 5-minute break and we come back after that and then we get into self-attention and the transformer architecture. Okay, guys. See you guys in 5 minutes. All right, Betty.
Oh, it's over the newspapers. Are you telling me I should wait until summer starts?
Which one?
For the newspaper. So should I wait until that?
Just wait a week. Just wait a week and then we'll start.
Okay.
But in the meanwhile, shortlist your topics.
Okay.
Think what you want to work on. That will keep you entertained. It's not that easy to come up on
Yeah.
it. So get really busy thinking of what you want to work on.
Okay. I'll see you on Sunday. Bye.
Yes. That's it. All right, guys, we start in 10 seconds, 10, 15 seconds. Please come back.
Because if I did actually that blocks, I can actually see it going on the rest of the other than seeing it on this one. Remote from home.
Yeah, it's against them.
It's
No, even VS Code is fine, the state score is against them, it's another thing. With the SSS. Even the highest score also you can do.
I tried the scale and I just found it out. So far had to,
For this.
I ran into the problems. So I'm scared of it.
What is it? What?
We doesn't have a user.
You can get them a score.
You have
All right, guys, let's continue. I would like to move on to the attention is all you need paper. But before I do that, I would I'll mention one final thing that I will mention is, see, I said that the score function associated with the vector h is measured by its alignment to the context vector, isn't it? The dot product. But that's part of the story. People, every time you do something, people point out, hey, we can generalize it to something else. So one of the things people started realizing is, hey, why just multiply the context vector? Actually, let me write it the other way around. Context vector and the hidden state. What if we did this? Suppose we multiply the hidden state, rotated the hidden state, right? So now what will you end up with? Hi prime, some hidden state with some rotation. Well, not rotation, some transformation. Bring in a transformation matrix. And then you compute the score. Score I is context and W and H like HI prime. Dot product between this, which is the same as the context vector and WHI. A transformation applied to H before you do it. Why in the world would you want to do it? And the answer could be, yeah, because you can. Why not? Let's see if it makes the results even better, right? If you can sneak in a matrix transfer with its own weights here, in this weight matrix in here, why not? So this is the generalized scoring function.
What does it give you there?
In some situations, people claim that it leads to better results. Right? So, it's one of those things. See, none of us really know why transformers or why some of these things completely work, like down to the math and the theorem proving level, right? We don't. Even as I just took you through the discovery journey of how attention came about, how the journey from CargoNet, right, to attention is all you need, was a journey that was very empirically driven, experiment. Oh my goodness, this is all you need, right? So what is it, that architecture that it is? We are now going to do that particular architecture. And just to, as a preface, okay, no, why don't I load that paper and see what we can do with that? By the way, are you guys having fun? I'm just taking you a little bit through the history of it. I hope you're not getting bored with this. Let me see if I have it in my downloads. Attention is all you need. No, I don't seem to have this.
So after that weights matrix it's the weights that you get that gets trained.
Yeah, that gets trained. That's the whole idea. That if you can train the whole network, the network will all get trained through backpropagation. let's give back propagation an extra job to train the weights also, right? Let's stick in a weight matrix and let's go and
I thought back propagation's role is to adjust the weight, is it not true?
yeah, that is it. That is absolutely it. So
So can we say that, okay, anytime if you want to generalize anything, just to multiply with the weight and learn it?
yeah, I mean, see, wherever you have a dot product between two vectors, you always can have the temptation to first rotate the vectors a little bit, or not just rotate, transform the vectors a little bit, and then the question comes, hey, why transform? And your answer could be, why not? Let the machine find out if it is any good. If it is no good, then the machine will learn that the weight vector should be a unit diagonal matrix, isn't it? 1, 1, 1, 1, 1. Right? Means no transformation needed. But why not generalize it to throw in a transformation while you're at it? Right? Who knows? We may need it. That's the way you think in these things. That if you discover a degree of freedom, if you discover that you can do something, then the temptation is very high. Why not do it and see what happens? It's common sense after that, right?
So only transformation, no activation.
No activation, just transformation, just a linear transformation. That's that. So, all right, folks. Now I'm going to take you to this paper, which is Attention is All You Need. It's a celebrated paper. And much has changed. See, when people came up with this paper, and these are now big luminaries, and it's always referred to as Vaswani et al. You see all these guys from Google Brain, Google Research, University of Toronto, and so forth. I think in the latest NVIDIA conference, they were brought together on the stage to discuss the discovery of the transformer architecture. I will post that video. It's a worthwhile video to watch, actually. Very, very interesting video. That's where I learned that the whole transformer could have been called carbonet till they threw away the convolution and the recurrence. So what is this paper about? I will read the abstract, and you will now, in hindsight, know what it means. But before that, I suppose I should explain to you what a language model means. I'll give it very briefly because this is the context of your bootcamp, and when you do the labs, etc., this is all very clear. Those of you who are doing the bootcamp. See, a language model is this. Imagine that you have a sentence: the cow jumped over the moon. This is a sentence. Now, if you translate it into any language, you would observe that in that language, what you cannot do is literally replace each word by its language translation. Isn't it? You can do it in your mind, convert each of these words to your language, and you realize that it doesn't work like that.
Doesn't make sense.
Doesn't make sense. So, for example, the cow. What is the Hindi? For example, if you those of you Tamil, I don't know. Most of you are Tamil here. So, guy. And the only reason I'm not using European languages is because I'm very weak at them. Super. Does this look okay? Does this look right?
Right here.
Those of you who know Hindi, this is the exact literation. And when you read it like this, you realize that the sentence doesn't even make sense in Hindi. How many of you know Hindi? So, right? It doesn't make sense. Whereas what you would want to say is something like this: guy, time, something like this. Would that be a correct statement? In now, if you observe this, it has fewer, order is different, and number of words is different. Do you observe these two things as true? Right? So you cannot work at the level of the words, because it doesn't work like that. And this would be, if you were to convert it to, let's say, Chinese, either simplified or traditional Chinese or Korean, it would be even harder, right? It would be even harder. Does it make sense? Right? So that's not what you do. So what you do is you ask a machine, you call it an encoder. You give it the sentence and you ask it to come up with a latent something called a hidden representation, a language model, language representation of it, latent representation of whatever was said. You encode it into that. Does that make sense? Right? And then you use a decoder to produce, let's say, the Hindi or Tamil or French version, the French version of the text. A sensible French or English, or Hindi or Tamil version. Does that make sense? So the in-between state is you take the essence of what was said into a representation that can be decoded. Now, if you think about it, that happens all the time. See, you and I are talking in terms of sound. But when we write a sentence like this, the written language itself is an encoding, a language representation. Isn't it? It captures the essence of what was said as sound. And it's a pretty faithful representation. When you say the same thing, your intonation, your accent, your voice may differ, but the substance of it will remain the same. And that was the whole purpose of coming up with a written language. And so written language is the first, in a way, a language model that you can think of, that mankind came up with. Isn't it? I say something, you write it down, and then now you can say it on your own. You can, but not only can you say it on your own, you can summarize it. You can summarize it. You can translate it. You could do other fancy things. For example, you could come up with named entity. You can find parts of speech recognition. You could do named entity recognition. Oh, well, nowadays generate image, right? But let's stay with just language for the time being, because this paper didn't go into multimodal. You could convert it into poetry. For example, if you so chose.
Asif, can I ask a question here on this?
Definitely.
Okay, so then, this assumes, Asif, to use your example of the cow jumped over the moon, this translation to Hindi, that cow, the word in English, and guy, the word in Hindi, get mapped onto this roughly the same vector space, right? Only then this works, right?
No. Don't think vector space. We are saying that the entire sentence, not at the level of the word, the entire sentence becomes some latent representation.
Correct.
Right. And you don't know, in the abstract, you don't know what it is. All you know is some latent, like for example, you and I are speaking. When you convert it into words and write it, what are you doing? You're creating a language representation of the sound, the semantic content in the sound, isn't it? I'm talking to you. If you happen to be taking notes, you're translating, you're converting or encoding the sound, my voice, into text. That is a language representation. Now, given that language representation, it opens up a whole host of possibilities. With a good decoder, you could translate, you could summarize, you could do parts of speech, you could find if there's a contradiction in what I said, consistency check. You could classify whether I spoke computer, like was I speaking neural nets, or for example, was I speaking Shakespeare? Right? And so on and so forth. Or you could do many things. You could do emotion detection, a sentiment analysis. You could do sentiment analysis, positive, negative, what sort of sentiment. You could do a whole host of things. Forget about computers. Just when the text is written, somebody reading the text on a page can do a whole variety of downstream tasks by reading the text, isn't it? We as human beings can do it.
Correct.
So,
yeah, go ahead. So you got that, right? So the text, the written word, therefore, is a language representation of the voice, of the spoken word. That is it, as simple as that. And writing it as the written word is the encoding. And someone, for example, reading it, just speaking it out loud in their voice, is decoding it into their voice. The simplest form of decoding that you can think of. Vasanthi.
yeah, would you be able to create a new language
Out of that?
out of this?
Hold that question. It's a very beautiful heart. So one question that I got is, can the machine use it to create its own language? Well, literally this thing that you have, the hidden representation, when the machine is efficient and well trained, it is saying, okay, the input isn't too inefficient, too long a thing. I have a very efficient representation of what was said. And when you look at it, you will be surprised how efficient and tight a representation machines come up with. And still they are able to decode from that. Very much like an encoder decoder. Remember, for images, it could reduce the image down to a very low dimensional space and then decode it back. What does that mean? The image for the benefit of Dumbo humanity is in a very high dimensional space. Right? It has a lot of redundant information, but the machine must be having private thoughts. What unnecessary? I'm just obviously putting an anthropomorphic perspective on it, but
Not maybe just encoding in a different compact way.
In a compact way, it's the same thing. Encoder, decoder, things like that. So a language model is, see, in many ways, there's a strong parallel between that. What does an encoder, decoder do? Input goes in, you have a latent representation, and then you decode the latent representation. Encode, decode. It's very similar to that, except that you don't use this kind of a symbol. But let's use it. Why not? Right? You come up with, and you give it a set of tokens, right? Words, token T1 to TK, and then you have Z1 to ZK. This is your hidden representation. Right? It comes up with latent. So long as it captures the essence of what was given, it's a latent representation. In the case of languages, that latent representation is called a language representation or a language model. Right? A machine that can do that, come up with efficient and good representations of language, is a language model. That is the concept of a language model. That's a language model.
So what the base for this? Like all languages are being abstracted into this kind of like
Yeah.
relations and then use that abstraction to get this vector.
That is right. That is right. So now let's read it and we'll see the thing. When you see how this works, right? A very clear realization. In this course, because I didn't cover RNNs, so it's a little bit abstract. We'll use this paper itself to make it much more real. So let's read the abstract. These are also called sequence to sequence models. Sequence to sequence. Why are they called sequence to sequence models? Because sequence of English words go in, let's say, and a sequence of, let's say, Tamil words come out. Isn't it? So these are called models, sequence to sequence. These are all words. With that, let's read them. What the word, and I'll read the abstract very carefully because it's a landmark paper. The dominant sequence transduction model, another word of saying sequence to sequence. What does transduction mean? Well, it's a word that sort of transforms in the conductance of the information as it passes through. That's one sort of an intuition. Are based on complex recurrent or convolutional networks that include an encoder and the decoder. Encoder decoder is a no-brainer. Right? We are modeling encoder, a language model, sequence to sequence model. All have an encoder decoder. The only degree of freedom you had is you could implement it using either a CNN or a RN. That's what they are saying. The best performing models also connect the encoder and decoder through an attention mechanism. Did we talk about whatever plus attention makes it better? That's what they are referring to. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Hey, by the way, I don't know, when did the Transformer movie series start? You know those kids?
Yeah.
I'm curious. It predates this paper, isn't it? That was the,
Yes, absolutely. Yeah, 2011.
Before that. Okay. So they call the architecture Transformers. And well, obviously they weren't inspired by the movie. At least they didn't say that. It would be fun, right? Well, they are Transformers, but Transformers are very generic word. They transform one thing to another. On attention, dispensing with recurrence and convolution. And this is the word based solely on attention mechanism, dispensing with recurrence and convolutions entirely. That's it. That's it, the theory. All they're saying is that you throw away all of that from the cargo, you throw away the convolutions and the recurrence, and you're left with ego, attention. Right. Experiments on 2 machine translation tasks show these models to be superior in quality while being parallelizable and requiring significantly less time to train. This sentence is the heart of what they thought at that time was the heart of the contribution. Only later on, as people unpack the transformer, they realized that the revolution wasn't just the fact that it led to more parallelization and significantly less time to train. They were looking at a neural architecture for reasons that we don't still understand is profoundly powerful. We still are trying to figure out why is this architecture so very powerful. We don't understand. We understand how it works. We don't understand why it works. You see the distinction? Right? So it's somewhat an analogy that I'll give you is somewhat like the Industrial Revolution, which started with the discovery of the steam engine. When the steam engine was discovered, people figured out how to make it work. Boil some water, burn some coal, boil some water, have steam, contain the steam, have that pressurized steam go in and basically drive a spinning wheel. And you have a perpetually spinning wheel from that energy. Now you have textile mills, you have locomotives, you have steam engines running over the railway tracks. You have all sorts of things, steamships, whatnot. But why does the steam engine work? There was no theory of thermodynamics way back in 1811 when this fired up the Industrial Revolution. And there was no atomic theory properly. And certainly there was no statistical mechanism mechanics, explaining thermodynamics, and therefore explaining the steam engine. These things didn't exist. That took the better part of almost 100 years to come about. We are in a somewhat similar situation. We have the transformers. We know how it works. We have all sorts of architectures that hack it this way, that way, and make it better and better and better, make it bigger. Why does it work? Specifically, what are the laws governing it? Some bits and pieces we know, most of it we don't. So
we are still in the beginning stages.
We are still in the very beginning stages of it. And so it will be remembered, I suppose, if this, we are truly looking at a revolution as profound as the Industrial Revolution, this AI revolution, then there are a lot of parallels between the Industrial Revolution and the AI revolution. One of the most significant ones is this: we have no clue why it all works. Well, people think they have a clue, and generally, we have a lot of hand-waving arguments. It's like a Swiss cheese. There are parts we understand, and there are parts we don't understand. But we don't understand the whole picture.
Businessmen and engineers don't care.
Businessmen and engineers don't care, right? So, for example, it didn't stop the world from building trains and having, textile industries and all sorts of manufacturing. They just went ahead, and the same is happening today. So it goes on to say that it achieves blah, 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 blah. That, of course, is the normal bragging rights. We'll move on from that. Now, a bit of introduction. Recurrent neural networks, long shot, LSTMs, and gated GRUs, these are things that existed, have been firmly established as state-of-the-art. Actually, let's forget about all of this. Now comes the iconic picture. So you need here's the thing. You need an encoder. You need a hidden representation, right? Language representation. You need a decoder, right? So, except that this decoder is not like an autoencoder. Right? These have autoregressive, like they have back cycles, right? So this is one thing to remember, that there is a autoregressive nature to this thing. So this part is your encoder part. This part is your decoder part. Are we together? Now let's observe what they do. What you do is you take word. In those days, you take words. Nowadays, we just use the word tokens. To the first approximation, not quite correct. Treat a word and a token as synonymous. In reality, it isn't like that. For example, the word become and becoming or became, right? Or so let's just say become and becoming. All right, run and running. Right. So you realize that this is the root word. Sometimes people break it up here. Right. Think. So ing tends to be all over the place, right? So what people do is they treat the token ing as a token, and they will use the word think as perhaps another token. They will think of the word big. Well, you get the basic idea, right? They will have prefixes and suffixes and so on and so forth. So those are called tokens, but I won't go into that. Let's do the first approximation. Think of tokens as words and punctuations. Right? Not quite accurately, but the intuition is token punctuation. In reality, it's word pieces, right? And punctuations. Punctuations like question mark, full stop, etc., etc.
So just fundamental question: when we humans, brains, kind of learn a language, we first understand the words, build the vocabulary, and then we put that vocabulary together to be, and make a sentence. Is this network learning the same way? And it looks like it's different. It's not
There is a parallel, and I'm coming to that in a minute. Hold my thought. Vasanthi.
Yeah, is tokens a word or lesser than a word? Or is it the same as
It could be a word, a punctuation, or a part of a word piece. For example, thinking word will be broken up into think and ing, two different tokens, word pieces.
So this is not the same as what we called as a generic sentence.
The cow. So suppose let's say the cow jumped over the moon. So if you look at the word boundaries, this is a word, this is a word, this is a word, and this is another word piece. These are word pieces, right? And this is a word, I hope. This is a word. And not a word, a token. And this also is a token. Oh, sorry. This also is a token. So how many tokens are there? Let's count the number of tokens here. 1, 2, 3, 4, 5, 6, 7, 8. 8 tokens. This token is special. It's called ED. Means it has no meaning unless it is prefixed by another token. It's a suffix. Come again? No, space is not a token. Are we together? So now comes a part that we have to know. So a little bit of preliminary. What you have is you take a fixed dictionary. Always in a language. Your dictionary will have, and people often refer to it as a token size. If you notice, for example, the conversation about the latest Llama 3 is, it is using 128,000, right? Token size, as opposed to 32,000 used by previous models and so on and so forth, Llama 2 and so forth. What they mean is actually, I don't know what they should have perhaps used, in my view, the word dictionary. Dictionary size. The size of the dictionary is the size of the number of words in it, number of tokens recognized. No, it is literally a dictionary. Like, as in, you remember in the ancient days, there used to have paper dictionaries. You would have words and you would have the meanings associated with it. That's quite literally that.
We have lookup instead of lookup.
Exactly. The only difference is, suppose you have a dictionary starting with the word, let's say, aardvark, right? Somewhere around this is the word, let's say, ages. Way down there, and here's the word cow, and here's the word kangaroo. And way down there, let us say that there is a word zephyr. And there are a few more words. What you would do is, to each of these words, and then there are tokens also, like, for example, full stop, question mark, exclamation mark, hash mark, blah, 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 etc. So this is your comprehensive collection of tokens that you consider valid, is a dictionary. Is the set of valid tokens in the language. But you say, well, you know what? The moment you create a dictionary, there's always a bigger dictionary, isn't it? So how many of you have had the experience of not finding a word in a dictionary and saying, there is no such word, especially if you're playing boggle. And then your opponent brings a bigger dictionary and shows, look, here is the word. Any hands? Okay, so that is it. So in other words, any dictionary is finite, and there'll be words outside the dictionary which are still valid. So what you do is you reserve a special word, unknown. You can keep a special token and assign all of those words not in your dictionary to that. So when I was a kid, in a bit of personal experience at aggregation, was in a boarding school, like, residential school. And it was an old British legacy. And our headmaster, every morning he would come up with a new word. He was trying to improve our vocabulary, word of the day. And he would throw us a word and ask, who knows the meaning? And obviously, most of the time, none of us knew. None of us was that interested in at that time doing it. I remember being in the 6th grade, and then he would explain the meaning of the word. He was obviously trying to improve our vocabulary, and I remember him with great fondness because he did do that. But after a little, so I just joined the senior school, coming from the junior school. He was the headmaster of the senior school, and then after a little while, I thought, isn't it like a Groundhog Day kind of a situation? Well, the Groundhog Day movie hadn't come out then, but very repetitive. Every morning is the same ritual. One word and no one knows. So I thought, okay, what do we do? In school, we used to be all given this Oxford pocket dictionary. I don't know, some of you may remember these little Oxford pocket dictionaries. And so I gave some time and memorized all the words in the Oxford pocket dictionary. So I felt, okay, now it's good. Except that every once in a while, he would ask for words that are not in my dictionary. And I was like, wow, this is not fair. So I went to him and I said, okay, where are you looking up these words? So then he showed me a dictionary, which was again an Oxford dictionary. It was called the Oxford Advanced Learners Dictionary. Does anybody remember that? Oxford, I don't know if you have been brought up in the British system, you may remember those dictionaries. So then I went and memorized the whole Oxford Advanced Learners Dictionary. And then I thought, okay, now I know all the words. Till I was one day walking on the, so I came from a very middle class background in those days. There was a tradition in India that on Sundays, on the street vendors, outside the big fancy stores, but on the street, they would be selling used books. And I encountered this beautiful looking, really thick tome of a book. And I was so fascinated. What is it? And it said something to the effect of unabridged Webster's dictionary or American language dictionary or something like that. Webster's. I'd never heard of Webster's, but it looked mighty and impressive. And I remember opening it, and to the delight, it had pictures. It not only had the words, it had meanings. It even gave some synonyms, and it gave some, did it give antonyms? I don't remember that. No, I think it did give some synonyms or something like that. And I was so fascinated by that book. I remember I bought that book in all its glory of thousands of pages. And I would spend many rainy days pouring through it. Little did I know that that kind of thing would later on help me, because when you come to US, you have to take this exam called Graduate Record Exam, GRE. And guess what? GRE was a walk in the park. The verbal, like which for us international people is the hardest, because it's language based, it was beyond trivial, because there was no word out there that didn't know the meaning, the synonym and the antonym of. So it is strange how, fun exercises can help you in life. But anyway, that's about dictionary. So you have dictionary, except that you maintain a dictionary in which you don't keep the meaning of words, but what you instead keep is this index. Let's say the index of this is 1 to 40, 900, or I don't know, 128, something like that. You can all the way up to, or maybe 900, 9,000, 9,251. By the way, these are values I'm cooking up. They are not the exact correct values. And then you go to 32K values, something like that. And so now what can I do? When I encounter this, the cow jumped over the moon. I can convert each of these, would you agree, to a number? And so what would I end up with? I would end up with a comma separated list of numbers. These are the token IDs. And so now I've reduced it to a list of integers. isn't it? And these integers, there's a long history to it, which I won't get into. There was a whole thing discovered around 2015, I believe, or was it 2016, called word embeddings. People found a way to represent words as vectors so that their meaning was preserved in the latent space. Those of you who are taking my bootcamp, of course, know that the state of the art has moved far beyond that. We do sentence embeddings. But in those days, word embedding was a great thing. And if you could convert each word, you could assign a unique word, a word vector to, let's say, king. You could have a vector for king. People began to notice some very interesting observations. You would take the king vector, you would minus man plus woman. And what they noticed that this was approximately equal to the queen vector. And this was a remarkable discovery that you could create. And there are techniques to do that. Word to vec, glove, etc., etc. There were a lot of, these are the famous ones, but there are lots of such embedding technology that people came up with to preserve, to in a latent vector space, capture the meaning of words. And when they did that, they could do very remarkable things. For example, this was one, for example. Okay? So
first they convert that into idea and then vector, right?
ideas in vectors and so forth. And there are ways of doing that. And very remarkably, they were doing that. So these were called word embeddings. Word embeddings. In fact, in the NeuroIPS of 2023 in November, the big conference for neural networks, the award for the paper that stood the test of time was given to the paper that discovered word embeddings. Well, you know, this is how compacted and fast-moving our field is. This is barely 2023. Less than 10 years have gone by, and you give it the paper that stood the test of time, right? As though only a few centuries have gone by. Right? So, well, that's that. Now, here comes the remarkable thing. So these are called word embeddings. So given a word, we can go to its embedding vector. That's a common thing. Now, guys, hold on. I'll take questions in a moment. So you can realize that for every word in your dictionary, there's a vector, isn't it? Now it turns out that one of the big discoveries of this particular architecture, the transformer architecture, was that you don't need to actually rely on word embeddings, pre-learned word embeddings like word to vec. You can actually let the machine learn the perfect embeddings through back propagation. Right? And the way it is relevant, and the reason it became very relevant is because words take on meaning from their neighbors. Right? For example, the word bank. What does it mean? River bank, financial bank, or your aeroplane banking? There are many. So words are, in other words, homonyms. They have many meanings sometimes. And the full meaning of a word is captured by the context in which it lives. Does that make sense, guys? And that is where you get to the attention part. So let's look at the main thing. You take the word embeddings, input embeddings are things like, think of them as word embeddings or token embeddings. If I take all the words, but then comes a problem. I need to remember their location. Where in the sentence were they? Does that make sense? I need to remember the position. So without explaining how, let us say that there is an algorithm that can add, given a word in the sentence, word in sentence, let's say its location is 1. I can convert it into 2 embedding vectors. One is for the word, whatever the embedding vector is, and to the position of the word the. E of the and the position of the word the. I can convert it somehow, right? I could do And then what you do is you concatenate those two. And I hope you're paying attention. I know it's getting late. It's important. You concatenate them. And then you do something which is most remarkable. You first bring in an attention head. What is the point of that? And I hope this one, we have the cow jumped over the moon. Or let's say that I take the other one, the sheep swam to the other bank and found something, found a pearl, found the other. She swam to the other bank of the river, let's say, of the river. Or she said, let me make this sentence more sensible. Swam across the river to the other bank. Just leave it as well. Now you realize that the word bank, the word bank, there's my highlighter. This word in and of itself is ambiguous. But the moment you make it pay attention to this, are you at all in doubt which of the three meanings of bank we are talking about? No, right? So that's that. Right? If you could make each word pay attention to the other words in the sentence, right, it would, in a way, become much more effective. Ambiguity would be lost. There would be better context or semantic richness in the whole thing. That is it. So what you do is, you suppose I were to treat each word, like let's say that each of these tokens, words, ultimately becomes embeddings and positions, etc. Ultimately, let us say that they became a hidden vector, h1, right? h2 to h, what was it, 9 or 10? I forgot. 8, h8. Right? Suppose it became h8, and then they became these. What we want to do is this word, I needed to pay attention. Each word is unique and is, in other words, a context. So given the word, let's say bank, which is h, whatever it is,
It's 9.
1, 2, 3, 4, 5, 6, 7, 8, 9, h9. So let me put h9. H9, you would agree, needs to pay more attention to h2. It needs to pay more attention to h3, and it needs to pay more attention to 1, 2, 3, h5. Okay. Why is 4? Yeah, 5. It needs to pay a lot of attention to h5. And the other things it can ignore, sort of thing. Right? Now, the more part is a degree of attention, a score. Right? So we can, that brings us to the attention score function. Right? So we can say the word that we are thinking about, let's call it the query word. Right? Here it is this word. Whatever word, it needs to pay a different degrees of attention, different score of attention, or the degree of attention to different words. So far so good, right? And then the attention that it needs to pay, in a way, attention that it would need to pay in the thing that we learned would be this, the query, the attention vector that you would, and like attention that it pays to each of the word total would be the vector itself. But if because this is a score, and I take all the vectors together, I sum it up. Yeah. each of the components, it would become a vector is basically, no, it would be, so think about this way. The score of I, if I do score of 1, H1, plus score of 2, H2, suppose I keep doing that, score of 9, H9, that is the word bank paying attention to itself. Right? What will I get? I will point in a certain direction, which is a composite of all of these words. Right? That's my attention vector. So this is a key insight. But there is one more step that we need to do. And that step, so far so good, right? I'm just developing what we developed about attention. Let's take it further.
So this S1 is known as score.
Score, yeah, score. The score that we learned a little while ago. Remember, score was a dot product between the context and a vector. I'm saying that the context is this guy itself, bang, the word bang, is trying to think, what am I? What am I? And so it goes and pays attention to all the words.
So is that H9 or HQ?
Actually, let me just put the, this is H9, that is becoming the HQ, the query vector. Actually, why do I use that? Let me just, in this particular case, use Q itself, Q vector. Is that better? Q vector. The Q, whatever the Q is, in this case, we chose the 9th vector. Bank, bank is trying to think, how do I color myself the right way, effectively? And it says, I can figure out how much attention to pay to all the words in the sentence. And therefore, each word in the sentence is paying, is sort of the context, looking for what score it has, how much attention it needs to pay to the other words. Isn't it? That's what it is.
So
and
Q is the context?
Q becomes the context.
How does the machine know to focus on that bank?
No. Each word is asking, what should I focus on? Each word says, I am the context. Yeah. I am bank. I am the context of this puzzle. I need to figure out what is the rest of the sentence about. So if I'm the context, every other word I can do a dot product with to figure out how much attention I need to pay to that word.
Q is the query or is it the context?
It is both the query and the context.
Both are same.
Both are same. Yeah. Now comes the fun part.
Here we define the bank as a context or within itself.
No. I'm just helping you understand.
Oh.
Like when you're trying to figure out what in the world is bank, bank becomes the context of your inquiry, isn't it? So you make it the query. Now the whole question is, it will acquire meaning, figuring it out what it is. Obviously, the word swam, across, and river is a giveaway, right? Giveaway in understanding which of the bank meanings you need, amongst other things, isn't it? So that is that. Now, what this paper found actually is something remarkable. It brought in one enhancement. It actually doesn't use one hidden vector for each word. It actually used two hidden vectors. It said, instead of HI, burst it out, and then see, we already have any HI can also become the query vector, right? So it would say that any word, suppose I have a word, break it up into a keyword, a value word, and a query word. Query vector, Q vector, K, Q, KV, Q. Now, what in the world is this? This part I explained. It's sort of like the context. When each word is searching, what do I pay attention to? It is the context. Makes sense. But what it says is that and they got this intuition from Google used to do what? Information retrieval? Search? Right. In search, what you do is you do this. You see, keyword search in a simplified manner is this. You have a word. It is basically a dictionary. So suppose you have a word, horse. You maintain a list of web pages that contain the word horse, etc. Right? But suppose you get the word horses, then horses, then what you can do? Suppose these words, you replace the word with a embedding, e-horse. You would hope that horse and the horses, because horses is not in your dictionary. Right? Suppose you don't keep plurals in your dictionary. If horse is there, you know which pages contain it. Right? Then what would you do? The e-horses, you create a vector embedding. You would hope that it would be very close to e-horse. Isn't it? These two would be very clear. So in other words, when you look up the thing, you look at degree of match in your dictionary. You may not get an exact match. Yeah? It's sort of a degree of match. One easy degree of match that you can think of is using a dot product kind of thinking. Make sense? Right? And so what they do is they say that the keys would be a vector. And in this terminology, the meaning or the semantic content, if you think of it as a value vector, then what you do is, suppose you have the query vector for bank, you want to see how much attention it has to pay to every word. In a way, it is like looking up, what am I? It is going to the key of the word I, doing the dot product and saying, okay, whatever the score is, score I times the value I vector. Right? This is what it is. So you can say that the attention vector for bank is basically this. The query vector for the bank, K, the K vector, the dot product of every word. I is every word, isn't it? Times VI, of course, and then you sum it up, sum up all the vectors, right? So whichever direction that final vector points to, like in this thing, this is what it is. Right? And so you get the attention. So how would you do that? You would take the embedding, like the embedding plus position vector. Let me just call this vector the input vector. Let me call it xi.
For each word, there will be like a 3 sets then.
3 sets, exactly. For every token, there are 3 sets. You burst it out into K, Q, V. But how do you burst out? This is a vector. How do you break a vector into some other 3 vectors? What you do is, this vector, now this vector may belong to certain dimension space, let's say n dimensional space. But this vector in the original paper, they made it belong to a 64 dimension space. This also belongs to a 64. Why? Because you're going to do a dot product. They better be in the same space. And this also, they made it into a 64 dimension space. Why 64? Because 64 is a nice number.
I don't understand what value there is.
See, the hidden state of a vector, right? They for a word, they decided that let's break it up into 2 parts. Key is sort of like, okay, value is the hidden state. But what they say that where the value is, let's think of a location. Just like in a dictionary, you look up a value by a word by its meaning of a word, right? Or dictionary by its keyword. So what they say is that given a word, break it up into the key vector, which is, think of it as a location, just as you would do in a dictionary, right? And value as the real thing, the actual thing, the actual hidden state. The thing.
Value like changing the definition of
that is the semantic concept. That's a way, that's one intuitive way. Not well, see, once you get used to this terminology, it sinks in. But for now, think of it like that. Right?
The location you always have a deterministic value.
Right.
Meaning how do you determine value for that?
Yeah. So now here's the question. Well, all of this is fancy thinking, but how in the world do you know the KQV? Right? And the query vector also. So the answer in machine learning always is let the machine learn it through backprop. Right? It's like, what? You have only one solution to every problem. Right? Let the machine learn it. Right? So what you do is you need to multiply it by a linear transformation because you're going from n-dimensional space to this. So there will be a query WK, WV, and WQ. So what will happen is that the same vector, this input, which is, let me call it embedding vector plus position vector is xi times WK, transformation applied to this will produce the KI vector, right? WV applied to same vector will produce the VI, the WQ xi applied will produce the QI. Are we together? When you do this plus, and now let's look at that.
How in the world is only K, only V coming from?
They just conjured it up. They say, okay, this is the way we come from Google, this looks like search dictionary. So let's not have hidden. See, the key insight was query part self-attention was okay. The interesting insight is they broke up the hidden state into 3 parts, query, key, and value. And they said one part, when a word is paying attention to others, it is the context, which is okay for attention mechanism. But the key insight is that don't have the other thing as just it, break it up into location vector and a value vector, 2 big things. Yeah. And that is the interesting thing. And then what do? Let's look at what they do. You have now for every word 3 things, right? What you do is at some point you go, you'll KQ. So the equation is K. Remember, let's look at this. What is the order of operation we are doing? And by the way, this is not look at this. First you multiply KQ, isn't it? So architecturally, you would take multiply KQ. Then it turns out that for no reason, but because it's practical, you divide it by square root of D. D is the dimensionality of the output, which is 64 square root is 8. And it's just for practical reasons. So that you have more well-behaved numbers. They don't blow up. You divide it. So that's not very important. That is this part. Right. Forget about the masking part. And then you multiply it by, you softmax it. Why would you softmax it? Because when you get this attention, this part, it turns out that this part, you don't want negative numbers. You're just saying how much attention to pay to each of these. You want only positive. What's the easiest way to pay different, like take a bunch of numbers and convert them into values from 0 to 1 and all of them adding up to 1? What's the easiest way? It's the most common way that we use, right? The most common way. So here comes your softmax, and this becomes your celebrated attention equation. This equation is the most celebrated equation at this moment in generative AI. This equation, now does this equation make sense, guys? Look at this equation. I broke it down and brought you to it slowly. Right. Now, this equation is actually in this paper, if I have to give, it's a wonderful paper, but if I have to give it one criticism, I would say that it is speaking to a very small cabal of people who already knew what this was. Isn't it? Right? Like you first read this paper and you stare at it, at least my experience was, and you're like, what? Right? It takes a long time to unpack it, and you have to go back many papers. You have to go back to the sources and then gradually decipher it. So a lot is packed actually. And then, so the thing is, what they found is attention is good. You create this attention head. So let me represent the attention head as this. So information goes in here, your values, the tokens. The cow jumped over the moon. Now notice that all the tokens going together. In fact, you can't sequentially do it. You have to do it in parallel because every word needs to pay attention to every other word. The beautiful thing is it's necessarily parallel, right? Big win. Then once it pays attention, you will end up with attention vectors, A1 all the way to A9, right? So they realized that if you did that, It's a good thing, right? But then they thought, okay, if it's a good thing, and then while you're at it, why not throw in some feed-forward networks also? Your standard dense layers. Right? Let's apply some transformations with activations also. Why? You need that for? Why do you need those layers? See, these are linear transforms, so softmax introduces some nonlinearity, but to really bring in deformations, good deformations, you need those. So this one unit is one unit of, it is called an attention unit, right? Or attention head. So now what can you do with attention head? One is good. What do you do when you come across one good thing?
More.
Do more. And how can we do more? We can do more by taking these inputs, putting one attention head, its output going to the second attention head, its output going to the third attention head, 6 layers deep. In the original paper, they kept on feeding this. The second attention would treat whatever comes out from the first attention head as its input. So you can sequentially pass it through this and have the result come out. But then they thought,
So
well,
from the second layer onwards, it's all like a hidden.
it's all hidden things, yeah, that you're treating. So that is why in the paper, do you notice that n times, and I think they mentioned somewhere that n is 6. Yeah, look at that. N is 6. And they thought, well, that is good. But if more is good, even more is better, isn't it? Right? How can we do some even funkier things with it? So what they realized is that
No, what is happening in the next set of layers? The first layer we understand what is happening. What is happening in the next set of layers?
the next layer is treating the words coming from the previous layer as though they were inputs.
Okay, fine.
And keeps on doing it.
What happens to it?
And what happens is attention now pays attention to other attention vectors. It gets funnier. And now here's what they did. They said if one tower, so this is one tower, I call this one tower. This is not a language that people traditionally use, but this is one tower, right? If one tower is good, why not many towers? Let's put one more tower here. Let's put one more tower here. Exactly the same. And the input that comes, the same input that comes, route it to this, route it to this, and route it to this. Right. So now you have in series and in parallel, right? You have parallel towers. So these were called multi-head. You call this one head multi attention. And what they would do is you have multi-heads now, head in parallel. And then what they observed is actually quite interesting. When you do back propagation, see, think about it. Now here's a conceptual thing to think about. How will a network react? When you give it things parallel paths, it's trying to minimize the loss function. Right? It is not going to mirror one tower in another, the weights of one tower in another. What will it do? It will say, I have so many knobs, let me use it efficiently. Right? So it will make one tower do one thing and another tower do something different. That's when it will, like one, for example, will focus more on the grammatical structure of the sentence. Another will focus perhaps more on the linguistic or the semantic structure of the sentence. Isn't it?
And this is how is it designed, or is it how the
No, they observed. They observed that was happening. Yeah. And these machines are insanely clever, actually. The fact that backpropagation forces them to differentiate in function. Right? It's like we have 2 hands. One is good for hammering, one is good for writing, kind of thing, right? It's sort of like that. These machines, obviously, that's what they will think about it for a moment, and you realize that that is what it will do. It will try to specialize functionality, yeah, to have the maximum bang for the buck or to minimize the loss function. And that's what it does. And therefore, that is the whole network architecture. The rest of it is history. If you read this paper, you realize that there are benchmark numbers, why self-attention. It talks about that. Now, the one part that I didn't talk about is the encoder-decoder part. This is the encoder. So the encoded value, you feed it into that representation, you feed it into the decoder. The only thing about decoder is that it is an auto-regressive model. These parts I'll talk much more in detail in the boot camp. But the main thing is that if you produce a token, so decoder is sequential. You produce the language representation, right? Think about it this way. Decoder will, no matter whether it's RNN, CNN, or it is attention, if I produce an encoded latent representation and I produce the word verb, guy, do you realize that I not only need the latent representation, the next word that I produce has to be informed by these two previous words. So I have to give it the latent representation as well as the words that I've produced to produce the next word, and so on and so forth. So that goes into a little bit more. Since we are out of time, I won't go into it. I cover this in considerable detail when we come to the boot camp. So this is your decoder part. It's a little bit taller, but if you look carefully, it looks more or less the same. Right. This is your encoder decoder, and this, folks, is your celebrated transformer. This is what started changing the world. It came out in December 2017. By early 2018, people really knew the world had changed. Go ahead.
That celebrated equation that you showed. Right?
Yeah.
QKV.
Yeah.
So that is called self-attention?
That is the self-attention equation.
That's not attention, it's self-attention.
It is, yeah. It is a special form of attention. See, it is attention, but applied in a specific way, KQ. Right? So I would say, yes, it is attention, but a specific form of attention called self-attention.
Because even funny now, usually started thinking.
What's it?
Usually already started thinking. Right?
Yep. It is. All right, guys, I hope it was fun. Any questions? I'll now open it up to questions. By the way, see, guys, this is a very dense, pretty long intellectual journey that I've compressed in 3 hours. But I hope it did help you understand or get picture. Use those wonderful videos to review the 3 blue, 1 brown. Most likely after watching those most wonderful videos, everything will sink in even more. And there are tons of resources. Jay Alamar's illustrated introduction to Transformers, very good. I put all those resources on your page. I will put them if they are not yet there. Do that. This is there. I already put it, yes. Okay, guys, so take this seriously. I wanted to end the course with the most important architecture. We have a final session. I will extend this architecture to BERT and to visual transformers so that it forms a segue to your boot camp. But it's pretty much the architecture that ends the course. We're not going to do new architectures. We are going to see uses of this architecture in the next session, the final session of this course. That's that. Questions, guys? Any questions? Or I think it's late night and everybody has fallen asleep.
I mean, it will digest.
Yeah, it's hard to digest it. That's what the right word is. Because you know what is happening, but how it works and what are the connections? Like what are that's the hard part to understand that.
Yes.
So get me the account there and I will just.
All right. Any questions, guys? Anyone? Anybody on Zoom still awake?
Asif, I see the word fertilizer in the code. Is that anything related to what you were speaking?
That's different. That's an old traditional breaking text into tokens.
So that word embedding is not used anymore.
See, nothing ever dies. They are still used, the traditional word embeddings, but in transformer architectures, you learn the embeddings. But word to word, glove, etc., they're still going strong, though not as perhaps.
So if there is a new word introduced in the dictionary, that there's in the current architecture, we have models still.
Yeah. We teach them. See, one of the interesting things is you just introduce a word. Let's say you introduce the word quarkus. It's not there in the dictionary. Beautiful thing about self-attention is it will figure out, you realize that a word can figure out its own meaning by paying attention to the words around it. That is the power of self-attention. See, I could have replaced the word she swam across the river to the other bank with the word she swam across the river to the other kaboom. And you would still know that the kaboom means the other side of the river.
You probably you come up with this whole understanding.
Yeah.
But then as a human, you can correctly get it wrong.
Yeah.
You don't know.